Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 7. In this lecture, we'll discuss driven oscillations and resonance. These topics are covered in Chapter 15 of our textbook by Surway and Jowett. In our last lecture, we learned that in a realistic mass spring system, in addition to the spring force, there may be other forces, and that these forces can dampen the oscillations. For example, friction or air resistance can take energy out of the system and dampen or reduce the oscillations. More precisely, the maximum displacement of the mass spring system is gradually reduced over time. We say that the oscillations are decaying or dying out as a result of these damping forces. To counter this effect, one may apply an external force that perpetuates the oscillations, that keeps the oscillations going. This external force can take many different forms, but it is usually periodic. In other words, it's a force that is repeated over and over again. When a periodic external force is applied to an oscillator, it is said to be driven or forced. So when we talk about a forced mass spring system or a driven pendulum, for example, we're talking about systems to which we're applying an external force so that the system can continue oscillating in spite of damping forces. The driving force can take many different forms. If you're talking about a pendulum swinging back and forth, the pendulum might eventually decay, the oscillations might decay, and so to keep the pendulum going, you might simply give the pendulum a push. You would probably have to repeat this push every few seconds. So every few seconds, you might come in with your finger and give the pendulum a gentle push. This periodic external force that you are now applying to the oscillating system is called a driving force. You might be talking about a piston driving a wheel, as it happens in a train, for example, or an internal combustion engine inside an automobile. In that case, we would say that the piston is driving the oscillations. A little more precisely, the expansion of steam inside the cylinder or the expansion of a combusting gasoline mixture would be the driving force that pushes the piston and in turn drives the wheel. Later on, we'll be talking about oscillations in musical instruments, and we will see that the strings, for example, of a guitar are also examples of oscillating systems. They exhibit simple harmonic motion, and the musician who's playing the musical instrument is basically applying an external force to perpetuate the oscillations. So as you strum the strings or pick the strings, you're basically applying an external force that perpetuates the oscillations. In this lecture, we want to study the effect of driving forces on a mass spring system, or more generally on oscillating systems. When a driving force is applied to a mass spring system, or more generally to an oscillating system, energy is added to the system with each oscillation. So whereas damping forces remove energy from the system with each oscillation, a driving force tries to compensate for that loss by adding energy to the system. In general, the driving force can take many different forms, but in this class, we will always assume that the driving force takes this particular form. We will always assume that the driving force is a sinusoidal function, so it can be described using a sine function or a cosine function. We will choose to use the sine function. F sub d represents the driving force. This is the external force that's being applied. This could be, for example, the force of your finger as you push a pendulum in a periodic, repetitive manner. A sub d is the amplitude of that driving force. So A sub d determines essentially the maximum value of the force that is being applied. And the force is being applied in a periodic manner, like a sine function, and that function has its own angular frequency, omega sub d. In general, omega sub d can be different than omega. So we have the angular frequency of the driving force, and then we also have just plain omega, which is the angular frequency of the oscillations. Under the right conditions, they can be equal to each other, but not in general. So be careful to distinguish A sub d from A and omega sub d from omega. So how does this driving force influence or affect the behavior of a mass spring system? Well, to answer that question, we need the equation of motion. Essentially, we need a differential equation that helps us figure out how position or velocity change as a function of time. As usual, we basically use Newton's second law of motion. So this top equation here is essentially Newton's second law of motion. On the left-hand side, we have the net force acting on the mass, and on the right-hand side, we have mass times acceleration. Notice that there are now three forces acting on the mass. The first force is the spring force that comes from Hooke's law. The second force is the damping force, which we're modeling as a resistive force, so it involves a damping coefficient, and it's proportional to the speed of the moving mass. The third force is a new force, is the driving force that we are now applying to compensate for the loss of energy due to the damping forces. Notice that the driving force has a positive sign in front of it, whereas the damping force has a negative sign in front of it. So that's suggesting to you that one of them is basically damping or removing energy from the system, whereas the other one is driving or adding energy to the system. By rearranging this equation, we can put the equation in standard form, which is a second-order differential equation. This equation tells us that the position of the mass spring system is a function of time, such that when you take its second derivative with respect to time, you get this complicated mess on the right-hand side. You get the first derivative of this function times some constant plus the function itself times some constant plus some other sinusoidal function of time. It turns out solving the second order differential equation is quite complicated. This is the most complicated differential equation we've seen so far in these lectures. So we will not be able to write the precise solution to this differential equation. However, under the right conditions, this solution can simplify, and our goal for the rest of this lecture will be to better understand that simplified solution. So we're trying to understand the precise behavior of a damped and driven mass spring system. To understand that behavior, we wrote down a differential equation. Unfortunately, solving that differential equation is quite difficult. The saving grace is that those difficulties are often associated with the initial oscillations or initial behavior of the mass spring system. In other words, those difficulties are often associated with the early time of oscillations for the first few seconds or first few periods. After that, the solution turns out to be somewhat simple and easy to write down. A little more precisely, we can say that when time is approximately less than 10 periods, here capital T is the period of the driving force. So for time that is less than approximately 10 periods, this solution is known as a transient response, and it is quite difficult to write down, but it is behavior that is transient, meaning that it passes through, it doesn't stick around, it does not persist. That complicated solution is eventually smoothed out in a sense, and so that after approximately 10 periods, the solution settles into a nice sinusoidal form, something that we call a steady state response. And the steady state response is easy to describe. It is easy to write in mathematical form. It turns out we can say that the solution after about 10 periods have passed is simply a sine of omega t plus phi. So the form of the function is quite simple. However, there is a catch the amplitude, the angular frequency, and the phase constant can in general be quite complicated. A little more precisely, during this steady state response period, this late time behavior of the mass spring system, the amplitude is given by this horrendous formula here. This formula is telling you that the amplitude of the oscillations is related to the amplitude of the driving force. Remember, the amplitude of the driving force is essentially telling you how hard you're pushing the pendulum or how strong the driving force is. But the amplitude of the oscillations also depends on the mass of the system and the angular frequency of the driving force and the spring constant and the damping coefficient. So although writing the equation down is relatively simple, this particular constant in front is quite complicated to figure out. The phase constant is also somewhat complicated. It turns out to be given by this formula here. A tan is simply an abbreviation for arctangent, so the inverse tangent function. And as you can see, the phase constant depends also on the frequency of the angular frequency of the driving force and the damping coefficient and the spring constant and the mass. The only thing that's simple about this equation is the angular frequency of the oscillations. It turns out if you wait long enough, the angular frequency of the oscillations is simply equal to the angular frequency of the driving force. That's not true during the transient response. During that initial phase of the oscillations, you're pushing the pendulum and the pendulum is doing its own thing. The oscillator and the driving force are not yet synchronized. They are not moving in harmony. So they could have different angular frequencies. But after a few oscillations have passed, here we're putting the threshold roughly at 10 periods. After about 10 periods, we can say that the oscillations are synchronized with the driving force so that they are moving with the same angular frequency. To better understand the distinction between the transient response and the steady state response, consider this particular example here. We have a block, that's this green square, that is attached to a spring. On the other end, the spring is attached to a red block, which in turn, through this rod, is connected to a wheel. The wheel in just a minute is going to rotate, and as it rotates, it pushes and pulls on the red block. The red block in turn pushes on the spring, and of course the spring eventually pushes on the green block. To simplify the discussion, we could say that the red block is driving or forcing the green block. Notice how initially the motion of the red block is not at all synchronized with the motion of the green block. The motion of the green block is actually quite complicated. Those motions are plotted down here in this graph. The faint red graph that you see in the background describes the motion of the red block. The motion of the red block is very steady. It is controlled by the rotation of the wheel. It's a perfect sinusoidal function. The motion of the green block, on the other hand, is complicated. You can see it begins with large oscillations, and those oscillations are quite irregular, but eventually, after maybe 25 or 30 seconds have passed, the oscillations of the green block become quite regular. From that point on, we have a steady state response. So the first few oscillations where the motion of the block is quite irregular is known as the transient phase or the transient response, or just transient oscillations. And then the regular phase is referred to as the steady state phase. It's the steady state response of the system that we'll be most interested in this class. Remember that the transient response is the short-term response or the initial behavior of the system. It is not at all synchronized with the driving force, and it's a rather complicated function. It can't be described easily using a sine or a cosine function. The steady State response, on the other hand, is a long-term response of the system. It's the eventual final behavior of the system, and it is nicely synchronized with the driving force. Essentially, if you wait long enough, the green block begins to imitate the motion of the red block. Not exactly, but they will begin to move with the same angular frequency. From that point on, we can say that the system and the driving force are synchronized or operating in harmony with each other. So as we've seen, the behavior of a driven mass spring system can be quite complicated, but if you're willing to wait a few periods, then that behavior settles into a relatively simple steady state behavior. That steady state response can be described using a relatively simple trigonometric function. We have a sine function that basically describes the motion of the mass after a few periods have passed, and we saw precise equations for the phase constant and the angular frequency and the amplitude of that sine function. Now, you may have noticed earlier when you were looking at those formulas a couple of slides ago that the amplitude of the oscillations depends on the angular frequency of the driving force. In other words, as you're applying a force to the spring to cause the block to move, the angular frequency with which you're pushing is going to impact the amplitude of the motion. For some frequencies, the block will move a lot, and for some other frequencies, the block will move very little. So a natural question to ask is, what is the optimal frequency for driving an oscillator? In other words, what is the frequency that ensures maximum energy transfer into the system? Or what is the frequency that ensures maximum amplitude for the oscillations? To have a little bit of intuition about this question, imagine yourself on the playground. Imagine you're with a friend and she's swinging back and forth on the playground swing. You can model the swing as a pendulum. This pendulum will eventually decay in its oscillations and she will stop swinging back and forth. If you want to keep having fun, you want to push your friend periodically. And to maximize the fun, you want to make sure that her motion has the largest possible amplitude. To increase the amplitude of the oscillations, there are two things you can do. One is to simply apply more force, right? So give it a harder push every time that you push her. That's equivalent to simply increasing the amplitude of the driving force. The other option that you have, which is a little bit easier to accomplish, is to adjust the frequency with which you're pushing her. So you have to decide, am I going to push my friend once every second, once every 2 seconds, once every half a second? That period or that frequency of your driving force is going to impact the amplitude with which she is swinging. So we want to find out this optimal frequency with which you should be pushing your friend in order to maximize the amplitude. To answer that question precisely, let's look at this formula again. If you remember, we decided that the steady state response is described by a sine function, and the amplitude of that sine function is given by this complicated formula. This is not really a formula you need to memorize on an exam. I would give you this formula, but I would want you to be able to calculate it and know what it means. As you can see, according to this formula, the amplitude of the oscillations, remember the amplitude corresponds to the maximum amount of oscillation. The amplitude depends on a lot of different factors, but in particular, it depends on omega sub d, which is the angular frequency of the driving force. Omega sub d shows up here, and it also shows up here. So if you change omega sub d, if you change the frequency with which you're driving the oscillator, you're going to change the amplitude as well. For what value of omega sub d do we achieve the maximum value of A? Well, this is essentially an optimization problem. You know how to find the maximum of a function from your calculus class. You can take a derivative of A with respect to omega, and set that derivative equal to 0 to find the maximum of the function. It might be a little bit easier if you just focused on the denominator. Since we have a fraction here, you can probably convince yourself that a is maximized when the denominator is minimized. So the smaller the denominator, the larger the amplitude will be. So it will simplify the algebra a little bit if you just focus on the denominator and try to find the optimal value of the denominator. And with a couple of pages of algebra, which we will not go through, you will find that the optimal frequency is given by this expression here. When the driving angular frequency is equal to this expression here, if you take this expression and plug it in here for omega sub d, you will see that a takes on its maximum value, its greatest value. So this turns out to be the optimal driving frequency. If your goal is to ensure maximum energy input and maximum amplitude, this is the angular frequency with which you should be pushing your friend, or the angular frequency with which you should be pushing this spring. This special frequency, this optimal frequency, has a special name. It's called the resonance angular frequency of the oscillator. So when you drive an oscillator at its resonance frequency, what you're in effect doing is maximizing the amplitude by choosing this optimal frequency for pushing or driving or forcing the oscillator. So let's do a practice problem with some of the formulas that we've seen today. A damped and driven oscillator is described by the following parameters. M is equal to 0.2, K is equal to 30, B is equal to 0.5, and the driving force is a periodic force, as usual, given by this formula here. Everything is in SI units, so we don't need to worry about any conversions. Calculate the steady state amplitude of the oscillator. So the initial response, the transient response of the oscillator, is going to be quite complicated, but we're going to assume that we have waited a few oscillations, and now the mass spring system has settled into its steady state response. Everything can now be described by a nice sine function, and we have an expression for the amplitude of that sine function. This is the equation that tells us what the amplitude is in the steady state response. It turns out solving this problem is mostly an exercise in plugging numbers into your calculator. This is a rather complicated expression, so you should get some practice putting this stuff into your calculator. And if you do that, you will find that the amplitude for the steady state oscillations is 0.488 meters. Perhaps the tricky part in answering this question is knowing what A sub d and omega sub d are. I've figured out those two numbers by looking at this equation here. Recall that in this class, we will always assume that the driving force will take this form. The driving force will always be some amplitude times the sine of some angular frequency times time. So comparing this standard form to the equation that's given to us, we can see that A sub d must be equal to 10 and omega sub d must be equal to 7. That gives us numbers for this A sub d and this omega sub d and this omega sub d. Plugging all of that in, you should get 0.488 meters. Part B of the same problem asks us to calculate the optimal or resonance angular frequency for driving this oscillator. So what we have seen is that when we drive this oscillator with an angular frequency of 7 radians per second, then the amplitude is 0.488. So the question now is, can I get a bigger amplitude? Can I change the angular frequency so that the amplitudes are larger? To answer that question, we have to find what the optimal frequency or the resonance frequency is. We have an expression, we have a formula for that. This optimal frequency is known as the resonance frequency, so I'm going to denote it as omega sub res. And it's given by the square root of k over m minus 1/2 b squared over m squared. You can plug in all the numbers and you will find that the resonance frequency or the optimal frequency is 12.119 radians per second. So the 7 radians per second that we started with was not optimal. If we increase the angular frequency, we can get a larger amplitude out of this oscillations. So let's end this lecture with a review of some of the concepts we've learned about. Hopefully you've gotten the impression that the notion of angular frequency is extremely important to oscillations. It turns out angular frequency is at the very heart of oscillating systems. If you know the angular frequency, from that you can calculate the period and the frequency. All three of those concepts are interrelated. So it's important for us to have a good grasp of the angular frequency of these oscillating systems. Unfortunately, there are at least 4 different types of angular frequency that you will encounter, and it's important for you to be able to distinguish the different types of angular frequency that there are. I've tried to summarize those on this slide here. The very first angular frequency that we encountered is often referred to as the natural frequency of the system. We can denote it as omega sub natural, although this subscript is often dropped. That's going to be equal to the square root of k over m. This is the angular frequency of a mass spring system that is not damped and is not driven. So it's a simple mass spring system. If there is damping, then we have a slightly more complicated formula. We call this the damped frequency, and we denote it as omega sub damped, although this subscript also is often omitted. You can see the formula here is a little more complicated, and you can also hopefully see that this formula reduces to this formula. If you have a simple mass spring system, then there is no damping, which means B is equal to 0, which means in that case, this entire square root will equal to this entire square root. So numerically, under the right conditions, the natural angular frequency can be equal to the damped angular frequency, but in general, that's not true. And then there's the driving angular frequency, which we've been denoting as omega sub d. This angular frequency is determined by the driving force. So if you're pushing a pendulum or pushing your friend on a playground swing set, then you determine what the angular frequency should be. The angular frequency with which you are pushing your friend is going to be omega sub d. If a wheel is attached to a spring, which is then attached to a block, the wheel is driving the block. In that case, the angular speed of the wheel determines the angular frequency of the driving force. Under the right conditions, the driving angular frequency can be equal to the angular frequency of the oscillations. In particular, in the steady state phase of the oscillations, assuming you've waited a few periods, you can say that the angular frequency of the system is equal to the angular frequency of the driving force, but that's only true for the steady state phase. And then lastly, we've encountered the optimal or the resonance frequency of a system. We can denote that as omega sub res, and that is equal to this expression here. Notice that omega sub resonance is quite similar to the damped omega. They have very similar formulas, but of course they're not exactly the same. There's a 4 here and there's a 2 here, so make sure you're looking at these subtleties and distinguishing these different types of angular frequency. And that is the end of this lecture. Thank you for your attention.